Hello everyone, I'm Norman Wildberger. This is our last video in this topic of the perspective image of a square, problem number 18 on our famous math problems series. And today I want to go beyond the solution that I showed you last time, where we're trying to show that a given quadrilateral is the perspective image of a square by finding an appropriate point of perspectivity P. And the solution that I showed you, which is really a three-dimensional one like this, involves two parallel planes, and crucially finding this point involves taking the meet of two circles built on these 4 points with diameters w, w prime for this circle and v, v prime for this circle. And I explained to you that there's an algebraic aspect or even a number theoretical aspect, which is quite interesting. And so this brings into focus a very broad arena of investigation, namely number theoretical aspects into classical geometry. Now, this is perhaps surprisingly not so well understood these days because our modern perspective finesses these number theoretical issues by sort of working in a real number framework, or sometimes a complex number framework, where the underlying number system has all these sort of miraculous completion properties that solve a lot of number theoretical questions. But if we separate ourselves from that wishful thinking kind of arithmetical story, then a lot of number theoretical issues come into focus, and the connection between geometry and number theory is a very rich one. So we're going to explore a little bit of that in this direction by just looking at this very concrete problem. Of the various constructions that were used in the solution, there's really only one which is algebraically subtle, involving a possible number theoretical issue, and that's the meet of these two circles. Okay. All the other things involving straight lines and their meets and joins of points and so on is completely sort of a linear story, and there's really no subtleties involved in that. So when it comes down to, however, this question of the meet of two circles, we can make some more precise measurements by shifting from a synthetic view of geometry to a more modern analytic or algebraic point of view. And this is parallel to the shift from the original Euclidean geometry to the more analytic geometry of Fermat and Descartes. Nowadays, propelled even further by the growing importance of linear algebra. Okay, so let's have a look at this kind of situation, but in an analytic context. So let's orient things so that we're still kind of in a three-dimensional situation. So here's 3 dimensions, x-axis, y-axis, z-axis, and we're going to be just concentrating on the yz plane, which you can think of as being this plane here. Okay, so maybe this is the x-axis coming out here, y-axis in this direction, z-axis in this direction. Okay, so we're looking at this plane here, which is the YZ plane. And we have 4 points, say on the y-axis, coordinates A1 and A2, and they are a diameter of a circle C1, and also B1 and B2, they're the diameter then of a second circle C2. So the first thing that we can do is we can cook up the algebraic equations for these two circles. And that's not hard to do because the centers are just the averages. So the center here is the point with y-coordinate a1 plus a2 over 2 and z-coordinate 0. So in the yz plane, just in this plane for now, the equation of C1 is y minus a1 plus a2 over 2 squared plus z squared equals the radius squared. And the radius will be the difference between the average and A2, or the average and A1, which is A1 minus A2 all over 2 squared. And in an exactly parallel way, C2 is going to have a similar equation with the A's replaced with the B's. So now it's a purely algebraic issue. We have these two quadratic equations representing these two circles, and we want to know, is there a common solution P? say with coordinates y and z. Can we find y and z that satisfy both these quadratic equations? Well, if we can, then there's likely to be two of them, because we can see geometrically that if that's a solution, then its reflection is also going to be a solution. Now, this kind of problem may very well depend on the underlying number system. So it will depend on our assumptions about the arithmetic upon which all of this is based. So let's go ahead and solve this problem algebraically, and then we'll see where the number theoretical aspects emerge. So first thing is to rewrite the equations a little bit, just expand them out and bring things to one side. So the first equation can be rewritten as a1, a2 minus a1 plus a2 times y plus y squared plus z squared equals 0. And C2 is the same kind of equations with the AI's replaced with BI's. So here are two quadratic equations in y and z. And our first step is to take the difference between these two equations, because then the quadratic terms y squared plus z squared, which are common, are going to disappear. So let's take the difference, say equation 1 minus equation 2. Then we have a1, a2 minus b1, b2, and plus the y term with coefficient b1 plus b2 minus a1 minus a2, because we're taking this one minus this one. And as I said, the quadratic terms will disappear. We just end up with a linear equation involving only y, which happily has a solution. Y equals a1, a2 minus b1, b2 divided by a1 plus a2 minus b1 minus b2. And what is the meaning of this? The meaning is that here are the two circles that we've determined that any point lying on both circles will also have to lie on this particular line. This is an equation of a line in this YZ plane. Right? The y coordinate is exactly this number. And that's a line which is actually important sort of geometrical line associated to two circles called the radical axis. If the two circles meet, like they do in this picture, then the radical axis is the line through those two meets. However, this approach works even if the two circles don't meet, okay? Then this is still a defined quantity and defines a line which is sort of intermediate between the circles, which has important geometrical properties which have been well studied. So we haven't yet solved for these 2 points, but you can see that we've simplified the situation somewhat, because now we have a linear equation that we can then use in addition to the quadratic equations that we already have. And in particular, we could take, say, one of these quadratic equations and replace y with this numerical value. Okay, so y gets replaced, the y squared gets replaced, and then we'll have an equation just involving z squared. So that'll then just be a simple quadratic equation in one variable z. Okay, so the equation that we get is z squared. If we bring the other stuff to the other side, there's minus a1, a2 times a1 plus a2 times y minus y squared. And this whole right-hand side is some big expression in the variables, and we can simplify it. The denominator will be this term here squared, and when we expand it all out and bring things together, we realize that there is a pleasant simplification or a nice factorization that results. So the answer, after we simplify this right side, is, and you can check this, it's minus a1 minus b1 times a1 minus b2 times a2 minus b1 times a2 minus b2. All over the denominator a1 plus a2 minus b1 minus b2, all squared. Now this is a very simple quadratic equation. So this is the simplest kind of quadratic equation, where you just have z squared equals something. And it has a solution when? It has a solution exactly when the something is itself a square. This is a very important point, okay? That maybe this thing has a solution, maybe it doesn't. It depends on whether this quantity is actually a square. If it's a square, then there will be a solution. In fact, there will be two of them because we can take the square root or its negative. Okay, there'll be two square roots sort of to speak of. So we can then summarize what we've learned. That the two circles C1 and C2 meet precisely when? Well, precisely when the numerator is a square, because the denominator is already a square. So this whole thing being a square is equivalent to the numerator being a square. So that's minus a1 minus b1, a1 minus b2, a2 minus b1, and a2 minus b2 is a square. So let's have a look at an example that sort of corresponds with the picture that I showed you before, where a1 is, say, at the point 1 on the y-axis, and a2 is at the point 4, and b1 is at the point 3, and b2 is at the point 5. Then what does this all work out to be? Well, we have a minus, an a1 minus b1, so there's a 1 minus 3, then an a1 minus b2, so that's a 1 minus 5, an a2 minus b1, so that's a 4 minus 3, and an a2 minus b2, that's a 4 minus 5. So there's a minus 1, there's a minus 2, there's a minus 4, there's a 1, and there's a minus 1, for a total of 8. So in the example that I showed you, with these being the points on the y-axis that are used to build up the two circles, we can conclude that, well, the two circles meet precisely when 8 is a square. And now we have to ask, well, wait a minute, what's the arithmetical system that we're working over? Okay, so now at this point here, the number theory intrudes in a very simple and obvious way. The question is 8 a square or not? And over the rational numbers, it is not. So if we're working over the rational numbers, which is usually my preferred arena, we can say that these two circles don't actually meet, even though they look like they do. Now, if you were working over some other field, perhaps your number system is a finite field. So actually, everything that we've been doing here does work over a finite field as well. In fact, over a general field. But over a finite field, whether 8 is a square or not is a number theoretical issue. Over some fields, it will be a square, and there will be a solution. Over other fields, it will not be a square, and there will not be a solution. Now, for those who are real number advocates, of course, in the real number world, 8 is a square because it's the square of the square root of 8. Okay, that's almost a tautological statement. And then you ask, well, what is the square root of 8? Well, you could get your calculator, you press the square root button with an 8 and it spews out some decimal digits. But if you actually check, that's not really a square root of 8. It's only an approximate square root of 8. The true square root of 8, whatever that is some infinite decimal that goes on to the boundary of the universe. And at that point, it's just gotten going. And then it keeps on going forever and ever. And, in my view, this is not a proper object of consideration. But I differ on this point with most of my fellow pure mathematicians who like to contemplate these things. And who think that a little symbol, a little squiggly symbol like this, with an 8 under it, is a bona fide mathematical object in a pure sense. I don't believe that. Although I'm quite happy to accept the applied mathematician's point of view, which is that, approximately square root of 8 is what you get when you perform the calculator operation. And that effectively, that's close enough. So that's fine. But from a pure mathematics point of view, it's not an exact concept. So you can see that the number theoretical aspect is coming into play here. But when we think about it a little bit deeper, we realize that actually the original configuration, right, was three-dimensional. So if we go back to our original configuration, we had this plane involving our quadrilateral, and then we were free to choose this plane here, as long as this object plane ended up being parallel to it. So it's not as if we are forced to have this thing horizontal and this thing to be vertical. It could be that we could change the position of this plane as long as it goes through this y-axis. That means that actually there's a three-dimensional version of the problem I've just shown you, which is very relevant. So let's have a look at that. So that's what we get when we look at things in a three-dimensional picture and say, okay, on this diameter from 1 to 4, there's actually a sphere that we can construct. So we replace the circle C1 with, say, the sphere S1, and the circle C2 with the sphere S2. Then the meat of those two circles is going to be along not just a line, but actually the plane given by y equals, in this case, 4 minus 15 over 5 minus 8. That's the calculation. A1, A2 minus B1, B2 over A1 plus A2 minus B1 minus B2. That's 11/3 in this example, right? So it's just a little bit to the left of 4. So that's now a plane, and that number that we needed to take a square root of, which was 8. Okay, the denominator was this thing here squared, so that's 9. So this circle, which is now representing the potential meat of these two spheres, is given by the two equations. Y equals 11/3, that's the plane, and x squared plus z squared equals 8/9. X being in this direction, z being in this direction. So actually, to find a point on this circle, a common point of intersection of the two spheres, is easier than to find a point on the intersection of the two circles, because we have this extra degree of freedom. We don't really have to solve z squared equals 8/9. We have to solve x squared plus z squared equals 8/9. So it's a question about whether 8/9 is the sum of two squares, rather than it being just a square. Okay, so let me remind you of a famous result of number theory that says that a natural number n is a sum of two squares, precisely when it has no prime factors p, which are congruent to 3 mod 4. So like numbers like 3 is congruent to 3 mod 4. 3 is not the sum of two squares. However, 5, which is congruent to 1 mod 4, is a sum of two squares. It's 2 squared plus 1 squared. 11, that's congruent to 3, so it's not the sum of two squares. While 13 is congruent to 1, and so it is a sum of two squares, namely 3 squared, which is 9, plus 2 squared, which is 4. Okay, so that's the general kind of thing. And so it turns out that you can extend this in a reasonably easy way to rational numbers, and in this case, 8/9, well, the prime involved there is prime is 2, and that is not excluded by this quantity. So it turns out that we can, in fact, solve this equation. It's not too hard to do, and we get 2/3 for x and 2/3 for z. So if we square this, we get 4/9. We square this, we get 4/9. So 4/9 plus 4/9 is 8/9. So we're able to solve this equation, and we're then able to find at least one point which is on this circle of intersection of these two spheres. Okay, so there's a number theoretical aspect here. Going to 3 dimensions makes it a little bit more sophisticated. But I don't want to go too far in this direction. I don't want to explain this further, because actually the original problem that we have has a rather special nature. And there's some particular magic that appears with the actual perspective of a square problem. So in the original perspective image of a square solution, these 4 collinear points that we are building the circles from, they are not just an arbitrary set of collinear points. Okay? They are very important because they form a harmonic range. I remind you that that means that their cross ratio happens to have the value -1. Okay? And I remind that's because these 4 points are obtained by taking the sides of this quadrilateral, and where these two opposite sides meet, where these two opposite sides meet, so those are 2 of the points. And the other 2 points are where that horizon formed by those 2 things meet the 2 diagonals. Okay, so that's a very important special case. So these 4 points are not just arbitrary, they are a harmonic range. Another way of saying it is that W and W prime are the harmonic conjugates, or harmonic conjugates with respect to V and V prime. And what does that mean algebraically? Well, here I remind you is the formula for the cross ratio of these 4 points. A1 minus B1 over A2 minus B1 divided by A1 minus B2 over A2 minus B2. And now the condition that this is equal to minus 1 can be rewritten because we have one fraction divided by another fraction, so we can kind of clear things. We can clear the denominators sort of twice. And we end up getting A1 minus B1 times A2 minus B2 equals, when the other stuff is brought to the other side, minus A1 minus B2 times A2 minus B1. The minus because of this minus sign that we're assuming is the cross ratio. Okay, now happily this looks very close to that numerator that we were getting in the general solution I showed you. Here's that numerator again, minus A1 minus B1, A1 minus B2, A2 minus B1, A2 minus B2. So if this condition is satisfied, then we can replace this with, have a look here. What are we doing? We're replacing the A1 minus B1 times A2 minus B2, replacing the product of these two terms with minus, actually, the product of these two terms. So the result is that we get the minus signs cancel, and we just get A1 minus B2 squared times A2 minus B1 squared. Or another thing that we could have done is we could have done the substitution the other way. We could have replaced these two terms, their product, which is the right-hand side here, with minus this thing here, which are the other two terms. And then we would get A1 minus B1 squared times A2 minus B2 squared. Remember, the existence of this point of intersection of the two circles depended on this quantity being a square, because the denominator of the expression was automatically a square. What we're seeing now is that in this harmonic range condition that's coming actually from our perspective image of a square problem, this crucial quantity is automatically a square. So that condition for having a solution is automatically satisfied algebraically. And so we can bring this topic to a satisfying close by understanding that the construction that we've been talking about actually works algebraically, not just synthetically. And it does so in a very pleasant way. So the theorem, we might say, is that if our 4 points, A1, A2, B1, and B2, form a harmonic range, then these two circles, C1 and C2, they actually do meet at 2 points. And the 2 points can be described with their y-coordinate and their z-coordinates. So here's that y-coordinate that we know, because that's got to be the value that we've found before. And now here are the z-coordinates. They are the square roots of the quantities that had squares on them. So we get a plus or minus A1 minus B2 times A2 minus B1 over A1 plus A2 minus B1 minus B2. And if we use the other expression, well, then we would get a different looking answer for the z-coordinates, A1 minus B1, A2 minus B2 over the same quantity. So these 2 points actually do exist algebraically in whatever field we're working. So this is a very beautiful situation now, that it no longer depends on whether something is a square or not. To go back to the picture, okay, if we position our quadrilateral that we started with in the plane of the x-axis and the y-axis, then what this is saying is that to find this point P, it suffices to use the simplest possible plane for this one here, namely the plane formed by y and z. And then the coordinates of this point in this plane here, in terms of y and z, are going to be given by one of these expressions. Of course, then this plane here will also have to be parallel to it. So I think we get a very satisfying kind of universal algebraic solution. And the algebraic point of view has, I think, elucidated what's going on. It's given us an important alternate insight into the geometrical aspect of things. So the synthetic and the algebraic really coexist to support our understanding. So we've introduced this rather interesting development that a lot of geometry is really dependent on assumptions about our underlying arithmetical system. And this leads very naturally to our next famous math problem, number 19, which is, in my book, the most important math problem of all time. Okay, so I'm not going to tell you what it is. You'll have to watch the video. And actually, due to an interesting wrinkle in quantum space-time, that video may already be in existence. But in any case, that's going to address a whole bunch of really important issues. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.